Have you ever stopped to think about the hidden rules that kind of run our world? Well, there's one in our calendar we see every few years, and today we are going to crack the code of the leap year. Think of it like a fun logic puzzle that we get to solve together. Okay, so this is our mission objective. It sounds super specific, right? We've really got two things to tackle here. First, we got to find every single leap year in that 25-year span. And second, we have to format the output in this exact way. So, you know what we have to do? Let's break down the clues. Now, at its heart, this isn't some impossibly complex problem. It's really just a simple printing challenge, but with a neat little logic twist. A couple of fascinating rules we're about to uncover and apply. To solve any puzzle, you've got to start with the most important clue, right? For us, that means we first have to figure out with absolute certainty what actually makes a year a leap year in the first place. And that brings us right to the core of this whole thing. This is the most important piece of the puzzle, the official leap year rule. So the official rule is basically a two-part test. A year is a leap year if it passes either the first condition or the second one. The first one's for special cases. If a year is divisible by 400, boom, it's in. Simple. But for most years, it's that second rule. It has to be divisible by 4. And, this is key, not divisible by 100. Okay, this is where it gets a little tricky and honestly where most people get tripped up. This century years, the ones ending in those double zeros, they really put that and not divisible by 100 rule to the test. This shows the rule perfectly. Let's take the year 1900. Sure, it's divisible by 4, but it's also divisible by 100, which actually disqualifies it under that main rule. Then you check the special case. Is it divisible by 400? Nope, so 1900 was not a leap year. But 2000, that was different. It passed that first simple test. It is divisible by 400, so it was a leap year. So how do we actually check for divisibility in a logical, computer-friendly way? Well, we use this little secret weapon called the modulo operator. It's that little percent sign. All it does is give you the remainder of a division. Think of it like leftovers. If you have 10 cookies and share them among 4 friends, you have 2 cookies left over. So 10 modulo 4 is 2. When we say year percent 4 equals 0, we're just asking, hey, are there any leftovers when we divide the year by 4? If the answer is 0, it's a perfect match. All right, so we've got the rule and we've got our tool for checking it. The next step is just pure methodical work. We got to apply our rule to every single year in our range. Now, to solve this properly, we can't just guess. We need a system. We're going to create a loop. We'll start at the year 2000, apply our rule, then move to 2001, apply the rule, and just keep repeating that year by year, all the way up to 2025. So this whole process boils down to a clear, repeatable method. It's really just a simple 4-step dance. Start with a year, apply the rule. If it's a leap year, we note it down, and then we just move on to the next one. We just repeat that until we hit the end of our range. Fantastic. We've totally solved the first half of the puzzle, how to find the leap years. But remember our mission objective? The second part was all about that specific formatting. And this is where a very clever little trick comes into play. This brings us to the final hurdle in our puzzle. We can find the leap years, no problem. But how do we get that formatting perfectly right? We need some way to know when to just add a space and a second year versus when to start a completely new line. And the solution is so elegant, you're going to love it. We just use a counter. We'll start a count at 0, and every single time we find a leap year, we'll just add 1 to our count. Simple as that. Okay, check out how this counter works its magic. All we do is check if the count is even or odd. So when we find our first leap year, 2000, the count is 0. That's an even number, so we just print the year. For the next one, 2004, the count goes up to 1. That's odd, and that's our signal to add a space, then the year, and then start a new line. For 2008, the count is 2, even again. See the pattern? Even, odd, even, odd. That one simple check gives us perfect control over our formatting. It's brilliant. And there we have it, the leap year rule, a methodical loop to check every year, and that clever counter trick for the formatting. We have all the pieces. So let's put this puzzle together. So here it is, the entire game plan from start to finish. We're going to create a counter and set it to 0. Then we loop from 2000 to 2025. Inside that loop, we check if the year is a leap year. If it is, we check our counter to see if it's even or odd to figure out how to print it. And then we just add 1 to the counter.
It's such an elegant and clean process that guarantees we get the right result every time. So after applying this logic to every single year in our range, we have our final result. All right, here's the solution to the challenge. And there it is, perfectly formatted, 2000 and 2004 on the first line, 2008 and 2012 on the second, and so on all the way down to 2024, which, as you can see, ends up on a line all by itself because there's an odd number of leap years in our range. Mission accomplished. And that's really the bigger picture here. This wasn't just some abstract puzzle. This is the very logic that keeps our calendars in sync with the Earth's orbit. It's a hidden rule running quietly in the background of all our lives. And it kind of makes you wonder, what other elegant hidden rules are out there quietly governing the world all around us?